Bismillahirrahmanirrahim. Our aim is actually to discuss about convergence criteria of the methods for solving system of linear equations. For the sound base, we will overview the convergence of fixed point method because every iterative method is actually the fixed point method or can be converted into fixed point method. So therefore, we would be clear about the convergence criteria of fixed point method. Fixed point method is also called the iteration method. And we can convert or build an iterative method such as for any given uh, function which is equal to 0, linear equation or non-linear equation. Uh, we just consider that it is a non-linear equation fx is equal to 0 and it can be rewritten in the form of x is equal to phi of x. We can easily uh, change the form of fx is equal to 0 in x is equal to phi of x, and later on we can generate an iterative method xn plus 1 is equal to phi of xn to find the solution of given equation. Similarly, if we have the system of linear equations or system of non-linear equations, they can be modified in the form of fixed point formulation such as given here and later on can be developed in the form of successive approximation iterative formula. We are interested to determine the condition under which the iteration method converges. We want to find the condition for the convergence of the fixed point method. Xn plus 1 is a sequence which can be generated by taking different values at each step for n. While x is equal to phi of x is the actual solution, xn plus 1 converge to x as n approaches to infinity. That if xn plus 1 is equal to x up to the number of significant figures, consider that xn is the solution to that degree of approximation. Let xi be the true solution. If xi be the true solution of x is equal to phi of x, then this relation holds. Then xi is equal to phi of x. And, the iterative formula will generate the first approximation as x1 by putting the value of x naught in the function psi. Now using equation 1 and 2, we obtain this relation. And this is equal to this. We know that mean value theorem allows us to write it as where xi naught lies between x naught and xi, between these two numbers, x naught and xi. Similar equations hold for successive approximations so that we can write as xi minus x2 is xi minus x1, as we know that xi minus x1 is equal to this, xi minus x2 will be equal to xi minus x1 pi dash at xi1. where xi1 be any number between x1 and xi. Similarly, xi minus x3 will be equal to this expression. These all are obtained by using mean value theorem. Here we note that xi naught lies between x naught and xi, xi1 lies between x1 and xi, and similarly xi2 lies between x2 and xi, and so on. We can obtain xi minus xn plus 1, which is equal to xi minus xn and phi dash at xin, where xin lies between xn and xi. These all relations are generated by using mean value theorem. Actually, these are the errors. Xi is the actual solution, while these are the approximations x1, x2, x3. At each step, the error is calculated here. Now we multiply all the equations and we obtain a relation 5 minus xn plus 1. This is the last equation, which can be written as in terms of x naught. So taking absolute value, we obtain this relation. If each derivative at different values of xi is less than or equal to k, where k is less than 1, then this error is less or equal to xi minus x naught kn plus 1. If we assume that these all derivatives are less than k, where k is less than 1, then this relation will be changed in such form, such an equality. And this will lead to 0 as n approaches to infinity. Here this error can be made as small as we please by repeating the process a sufficient number of times. Thus, the condition for the convergence is phi dash x is less than 1, because this error approaches to 0 when these all derivatives are less than 1. Therefore, the condition for the convergence is phi dash at x is less than 1, where x may be any value in the neighborhood of the desired root. Now consider the iteration formula xn plus 1 is equal to phi of xn, which is the fixed point formulation. If xi is the true solution, then xi is equal to phi of xi. Therefore, it can be written as which shows that the iteration method has a linear convergence. This slow rate of convergence can be accelerated in the following way. This is actually the order of fixed point iteration. Here we see that the power of xi minus xn is equal to 1 and k is any constant. Therefore, the convergence rate of the fixed point method is linear or 1. This can be accelerated. It is additional thing that we can accelerate the convergence by modifying this formulation. If we take these two errors and and combining we obtain this relation, and now cross multiplying we obtain this relation. From here we deduct xi in terms of various iterations. This is known as Etiquette's formula, and this approach is rapidly rather than fixed point method. Now we check the convergence of iteration method. Condition of convergence. We know that the condition for the convergence of iteration process for solving simultaneously equation f of xy is equal to 0 and g of xy is equal to 0 is this. We know that any method which can be written in the terms of fixed point formulation can converge if phi dash at x is equal to less than 1. Here we have the two equations, or we may have more than two equations. Then our formula will converge if partial f by partial x plus partial g by partial x is less than 1. Similarly, partial f by partial y plus partial g by partial y is less than 1. Because f is function of x and y and g is also the function of x and y. So therefore, these two relations are necessary for the convergence of the method. And this result can be extended to any finite number of equations. If here we have only two equations, therefore we have these two relations because these two equations involve only two variables x and y. If you have three equations with three unknown, then you will have three relations. For example, if we have the system of three equations with three unknowns, in fixed point form we have x1 as and x2 can be written as from the second equation, and from the last equation we can write x3 as. You can easily rearrange x1 in terms of x2 and x3, x2 in terms of x1 and x3, and similarly x3 in terms of x1 and x2. So the condition for the convergence are these three. Hope you will understand that if we have three equations, then there will be three conditions. If we have four equations with four unknowns, then we will have four conditions. By partial differentiation of above equations, we obtain these results. Putting these inequalities, we get 7, 8, and 9, these relations. If we add the inequality 7, 8, and 9, we obtain this relation. Which is again rearranged as in three brackets. This will be satisfied if this relation is 1 or a11 is greater or equal to the sum of these two terms, and similarly a22 is greater than a21 plus a23. These are the absolute values of the entries of the matrix. Similarly, we obtain a33 greater than a3 plus 1, a31 plus a32. So therefore, these are the diagonal values which are greater than the sum of the other values in a row. This is the first row and this value is the diagonal value, and the diagonal value is greater than the sum of the other entries. Similarly, this is the second row in which a22 is the diagonal entry which is greater than the sum of the two entries. And similarly, for the third row, we have this relation and the diagonal entry is greater than the sum of the other two entries. Hence, the condition for convergence is this: aii is greater than the sum where j varies from 1 to 3 aij, I varies from 1 to 3 and I is not equal to j. This is the comprehensive form of these above relations. For the system of equations, the condition reduces to this relation that aii, absolute value of aii, is greater than sum of aij, where I varies from 1 to n and I is not equal to j. Thus, the process of iterations, Jacobi or Gauss-Seidel will converge if in each equation of the system the absolute value of the largest coefficient is greater than the sum of the absolute value of all remaining coefficients in the equation. Hope you will understand that for these two or any other iterative scheme, for the convergence, this condition will hold that the absolute value of the largest coefficient greater than the sum of the absolute value of the all the remaining coefficients in the equation. And a system of equation satisfying 11 is called the diagonally dominant system. System will be diagonally dominant if this relation will hold for all rows in which the diagonal entry will be greater than the sum of the other all entries by taking absolute value. Now the next we will see the rate of convergence of iterative method. In view of equation 1, 2, 3, the k plus 1, the iteration. This is the scheme of iterative scheme. This scheme is related to the Gauss-Seidel method, because here we see that k plus 1 and there is k plus 1 on right hand side. If on the superscript there is only k, it may be Jacobi method, but here we see that k plus 1 is here and also in these two places. Therefore, it is Gauss-Seidel method. If we replace the value of x1 k plus 1, if we put this value here, we obtain this relation, and simplifying we obtain this. This is in terms of k. This whole equation is in terms of k. And similarly, x2k plus 2 will be in terms of x plus 1 and x2k plus 2 will be in such a way. Simplifying, we obtain x2k plus 2 minus x2k plus 1 as a21 a12, which is the coefficient of here x2k plus 1 and with this factor. In terms of error equations, this is the error, local error, the difference between the two consecutive iterations. This will decrease if this amount will be less than 1. This error will decrease if this amount is less than 1. This shows that these two terms are the diagonal entries of the matrix, coefficient matrix, and these are greater. If these are greater than the other entries, if A22 is greater than the sum of other entries, then it will be greater than A21, and similarly A11 be greater than A12, and this will be less than 1. If this will be less than 1, then the error will be reduced, and in other words, we say that a method will converge.